Hello, Bill again, and welcome to Module 6, Assuring Color Fidelity, Transmitted and Ambient Light Situations. Let's recap first what we did in Module 5. We learned sign shops learned to manage light through joint faces, mechanical joint faces, and perfected that process. Here we go. Well, we're into something entirely different, another area of sign making, and imposed on us in the early 70s was trend towards flat-faced signage, flat graphics. And this particular one, I think, would sum up this problem of ambient light and transmitted light being compatible and faithful to the design intent of a particular brand, in this case, Gulf. You've seen the other Gulf signs. You've seen them basically in black and white, and that orange became the theme, the all-orange service station with beige structures and support system. The trend in the 70s, because of the petroleum, the first energy crisis, was to save energy. And one of the ways in the sign business was to use mercury vapor. Mercury vapor provided some energy efficiencies, but most importantly, as opposed to 12,000 hours for fluorescence, the mercury vapor lamps gave us anywhere between 18 and 24,000 hours. And that was a plus. In this particular case, the Gulf decided they were going to pay for the extra thickness required, the 36 inches, to be able to get a UL qualifications for using mercury vapor lamps. And at the same time, they were going to make the changeable price panels also of the same color. Virtually everything had to be orange. The Alcan siding and the metal fabricators, the pre-finished fabrication, everything that had to be in orange had to work off a master chip. Everybody provided assurances and samples of their match to that particular color. And then once the service stations all came together, sign man brought in his signs, the siding guy brought his in stuff, the pumps were with the silk screened orange, and whatever. All hell broke loose because nothing matched. And why didn't it match? It's a thing called metamerism. I didn't even know that term existed at that time, but what it meant was that this is any color that on any surface will change its appearance based on the spectral reflectance, how light is absorbed by the paint and reflected through it. That's the behavior of the light waves. I borrowed this little diagram from the Ralph Mayer's book on artists, techniques, and materials. I recommend it to anybody who wants to take art painting, whether as an amateur or professional. It is the artist's Bible because it talks a great deal about the dynamics of light reflectance, light absorption, and it applies to just about everything. Some of the waves are absorbed, some are reflected, transparent or translucent substrates, some are transmitted and refracted, and in the case of the transparent or translucent layer, which affects us mostly in our industry, particularly when you think of second surface colors, it's the opaque or reflected. It looks like number 3 on number 2. Polycarbonate is an acrylic. We're going to mention it very briefly here because here again, it refers to the transmitted light and the spectral reflectance. 10 layers of quarter-inch thick acrylic versus 10 layers of quarter-inch PC. And the reason I'm bringing polycarbonate into this picture briefly, it's because this is about the time where polycarbonate made inroads into the sign industry as a substrate, as an alternative to acrylic. And one of the things that baffled sign people is why the colors look different. And here's an example. If you look through 10 layers of the acrylic versus 10 layers of PC, you would still see that red ball through glass or acrylic, but you would not see it through Tuff-Ak. I have an example here again. that's not too different from the Gulf situation. We can go back to the Gulf and talk at length about how that thing was resolved. Basically, they had to change the program or change, and they ultimately changed and were sold to Ultramar. This was a difficult situation, made difficult mainly because of the architects and designers in question that would not move or deviate from their obsession of working with Pantone colors. It is a nightmare for any sign man to work with Pantone because Pantone as a color reference source is used primarily for print matter and posters and so on. Very, very rarely can it work with sign colors or through some sign substrates for the simple reason Pantones are mixed and blended, and they are with the CMYK printed colors, which is red, magenta, yellow, and black. And that is why we have this difficulty. The lower colors that you see there have a great deal of black in that mix. Combined with the fact that the architect and the designers insisted on polycarbonate, we had a double trouble here. To resolve the issue, because he wouldn't accept acrylic, and I had made the strongest recommendation to him that with these colors, at the very best with acrylic, we would have closer match to Pantone. They insisted on polycarbonate. They did not wish to pay for molded sections of acrylic because the costs of the molds and making it would have been much more expensive. So I proposed break formed polycarbonate if they needed, and we experimented because nobody had break formed polycarbonate. The result was that it was a great success as a structure, as a fact, and the fact that it illuminated beautifully. The corners everything was illuminated, but the colors were wrong. Fortunately, I had made a sample, a 2-foot by 3-foot sample of all those colors, and I made the customer sign them. He accepted the fact that they would deviate a little bit, but in the illumination and the overall effect, it would be acceptable. What you see on the left is what they got, because you had to accommodate the illuminated version versus the non-illuminated version. The illuminated version came closest to the actual printed. This I took off one of their brochures. Incidentally, I had to struggle really hard to find these pictures. The designer in question, he kept that as a souvenir, as much, I guess, out of guilt as anything else, but he actually kept my old file, and those are actually my pictures. These are pictures, but this explains to you in general how this thing was made. From my understanding at the time, it was the first time that polycarbonate was break formed to achieve this. You could not break form it in 90 degrees because it would shatter. It would be too dangerous. So we break formed it in increments, in slighter and smaller radius in order to make that curve. And then joined them in the corners, as you see here, over and slipped over. And we slid this over a structure. That was the end product. This shows you a little bit of how this thing was assembled on site. When we evaluate light, we had to always evaluate it in terms of what is the transmission value of the pigmented material. Now you could extrapolate what I'm telling you here and apply it to vinyl, because vinyl is generally so we're not going to focus on vinyl because just about everybody does it and understands it. Essentially, the dynamics are more consistent. But in our days, when we worked with pigmented color, they did not all have the same transmission value. If you look at the bottom, and you look at any one of them, you've got the number, and you can actually see the percentage of light going through anywhere from 3%, 4% to a maximum something in the vicinity of 30%. So it fluctuated. So it was very important for us to put the correct light source behind these pigmented materials. Your glass room was the key player in this thing. And of course, here I'm talking about the very fussy architects and designers who were insistent that there you get color fidelity both night and day. So we would have, you see the numbers on the left, the extreme left, that's to designate the color of the pigmented color. And then what you had was the formula for pumping the right gas and the combination of gases to get the light, the correct light to shine through. Just another continuation of the previous chart. This was critical. And fast forward just briefly, I've been telling people in the LED manufacturers that because there are such inconsistencies in color temperatures of all the various makers of LED lights, that one of these days you folks are going to have to wake up and get back to this type of a system where you match the color temperature of the LEDs to the specific color. And for the first time, I heard recently, and I saw an example of it, is 3M decided to work with Sloan to develop just that kind of light source to match the specific color, or pigmented or vinyl color. In other words, it's no longer just going to be a question of you picking 6500K, 55, or 3000K, what have you, to match a color. No, you're going to be infinitely more specific and more closely loyal to that original color. We have issues in a sign business with regard to color temperatures of the light. And that goes back to something I did about 10 years ago. I got a little fed up with having 6 or 7 LED manufacturers come to me and say, this is a 6500K. And I kept looking at it. And I said, well, your 6500K is not US LED 6500K or Permlight or Sloan or GE. There's something screwy with your guys. What is your 6500K? And I went to the extent of making a little box. I used the Philips 6500K fluorescent as my control. And I put layers and I put lines of 6 different LED manufacturers. And believe it or not, through a 2447 acrylic, not one of them came close to the Philips 6500K that I use as a control. That doesn't mean that the Philips was 6500K and that was the perfect one. And in fact, CLAB, which stands for Commission Internationale d'Éclairage, and the LAB is the system that uses the way to measure color and color temperature. They are still debating to this day. When specifying colors, designers will refer to different sources as the match that they require under who's as a sample or as an example that we must abide by. One of them is color curve, and its color curve is based on the CLAB values. The objective of color specification systems, of course, is to order the arrangement to assure fidelity. This is not always possible, and we will get into another program where there was an attempt, the most successful attempt ever, to achieve this. CLAB, Commission Internationale, is the most commonly used color difference equation worldwide. It was used in 1976 as an improved cube root equation. L is a measure of the lightness. A is the old black to 100 to white. The quantities A and B, called opponent type coordinates, define the degree of its yellowness. This is the actual formula for how they achieve and they arrive and how they establish color values. And Munsell is a system of color notations. That's another one developed by A.H. Munsell. The American National Standards Institute and the American Society for Testing and Materials have incorporated the Munsell notation of their standards. This is the one that is the most often used, and the ones that you see when you see ASTM, they're usually the Munsell system. NCS is, generally speaking, more of a European approach. And of course, this is the nasty Pantone that drives the sign people crazy. Thank you, and looking forward to Module 7.